In this video, we will use the concept of the rate determining step to determine the factors that can affect the rate for an SN1 or SN2 mechanism. Then in the next video in this series, we will see how to apply this material to solve problems that are typical of what you might see on your exams. The concept of a rate determining step is an idea that I previously introduced in the series on SN2 mechanisms. Now, to understand these factors that favor or disfavor a reaction, we have to use the concept of a rate determining step. How would you define the term rate determining step? Here's the answer. The rate determining step is defined as the slowest step in a reaction. That would be the most difficult step in the reaction. Now, this is important because anything that affects the rate determining step will affect the rate of the reaction. That's why it's called the rate determining step. And anything that does not affect that rate determining step will not affect the rate of the reaction. Let's try to apply this concept to an SN1 reaction. Do you remember, first of all, how many steps are there in an SN1 reaction? Answer: there are 2 steps in an SN1 reaction. Question: what happens in those 2 steps for an SN1 reaction? Answer: in the first step of an SN1 reaction, the leaving group leaves the alpha carbon. Then in the second step of an SN1 reaction, the nucleophile attacks the alpha carbon. Here I'm focusing on the main steps that always occur in every SN1 reaction. Step 1, leaving group leaves the alpha carbon. Step 2, nucleophile attacks the alpha carbon. Here's an example of an SN1 reaction that we've seen previously. Now here's the question: which of those 2 steps is the rate determining step? I hope you'll pause the video and think about this. Which do you think is the rate determining step for an SN1? The first step or the second step? I hope you actually paused the video and thought about that. You should have been asking which was the difficult step. The difficult step will be the slow step. And for that, what's your most important tool for thinking about organic chemistry? The formal charges. I hope you were really trying to use formal charges to answer that question. For example, notice that this first step creates 2 formal charges. This first step creates 2 formal charges, a formal charge on the alpha carbon and a formal charge on the leaving group. Is that going to be difficult or easy? Well, we know that nature doesn't like formal charges, so it seems like this first step is quite difficult because it creates 2 formal charges. And then what about the second step? Notice that the second step eliminates 2 formal charges. The second step eliminated a formal charge on the nucleophile, and the second step also eliminated the formal charge on the alpha carbon. Well, nature likes it when we eliminate formal charges. So if a step eliminates 2 formal charges, that should be an easy, fast step. So I hope that you are able to use the formal charges to determine that the first step in this reaction, when the leaving group leaves, is the difficult, slow step, because that's the step that's creating 2 formal charges. Remember, what's your most important tool for figuring stuff out in organic chemistry? Formal charges. So when I asked you to figure out the rate determining step, I really hope you tried to figure that out by thinking about the formal charges. So we've decided that the rate determining step for an SN1 reaction is the first step when the leaving group leaves the alpha carbon. By the way, there's another reason why this is a difficult step. Do you remember what we're creating? This first step creates a carbocation. And we've learned that besides having a positive formal charge, we've also learned that a carbocation has an incomplete octet. We've also learned that a carbocation has an incomplete octet. Well, you should know that nature prefers atoms to have complete octets. Nature doesn't like it when atoms have incomplete octets. So that's another reason why this first step is a slow, difficult step. Not only is it creating 2 formal charges, it's also creating an incomplete octet. That gives us another reason why the first step of the SN1 would be the slow, difficult, rate-determining step. Now, why do we care about that? Because anything that affects this first rate-determining step will affect the rate of the SN1 reaction. And also, anything that does not affect this first rate-determining step will not affect the rate of the SN1 reaction. It's really helpful to compare SN1 to SN2. So now would be a good time to review what is the rate-determining step for SN2. I hope you'll pause the video and come up with an answer. What is the rate-determining step for an SN2 reaction? Well, that's almost kind of a trick question. Remember, there is only one step in an SN2 reaction. There's only one step in an SN2 reaction, so that single step is the rate-determining step. Here is an example of an SN2 reaction. There is only one step in an SN2 reaction, so that single step must be the rate-determining step. What happens in that single step? The nucleophile attacks the alpha carbon, and the leaving group leaves the alpha carbon. In the term SN1 or SN2, what does the letter S stand for? Answer: S stands for substitution. In both of these reactions, we substitute one thing in the former position of another thing. We substitute the nucleophile in the former position of the leaving group. For example, here, we substitute the bromine where the chlorine used to be. And here again, we substituted the bromine where the chlorine used to be. When you replace one thing at a certain position in a molecule with another thing, that type of replacement reaction is called a substitution reaction in organic chemistry. What does the letter N stand for in these terms? Well, N stands for nucleophilic. These are ideas we talked about earlier in this video series. Earlier we learned what what the S and the N stand for. In this SN1 reaction, something new is going to occupy the position where the chlorine used to be. And the new thing that will occupy the position is a nucleophile. So this is called a nucleophilic substitution for the chlorine. And again here, the thing that will occupy the position where the chlorine used to be, the new thing will be a nucleophile. So again, this is called a nucleophilic substitution. We talked about that earlier in this video series. Now, what do the number 1 and 2 stand for in these names? Well, how many species participate in the rate-determining step for SN1? Question: how many species participate in the rate-determining step for SN1? Well, notice that there's only one molecule participating in this step. Only one molecule is participating in this step. That's why this reaction has the number 1 in its name, because one species participates in this rate-determining step. Notice that the second nucleophile does not participate in the rate-determining step. Only this molecule participates. The term SN1 has the number 1 in its name to indicate that one species participates in the rate-determining step. For example, here, only this one molecule participates in the rate-determining step for SN1. This ion is not participating in the rate-determining step for SN1. So why does the term SN2 have the number 2 in its name? Answer: because for SN2, there are 2 species that participate in the rate-determining step. Notice that here, not only this molecule, but also this second ion, both of these 2 species, they both participate in the rate-determining step for SN2. SN2 reactions have the number 2 in their name to indicate that 2 species are participating in the rate-determining step. The 2 species here are the Br- and this chlorobutane. SN1 has the number 1 in its name to indicate that only one species participates in the rate-determining step. Only this tert butyl chloride participates in the rate-determining step here for SN1. The Br- doesn't participate until the second step, which is not the rate-determining step. All right, so now we understand where the different parts of the names for SN1 and SN2 come from. Remember that these numbers don't indicate the number of steps. Even though SN1 has the number 1 in its name, it actually has 2 main steps. And even though SN2 has the number 2 in its name, it actually has 1 main step. So we've summarized some important information about SN1 and SN2 here on the screen. Now let's apply these ideas to figure out the factors that favor or disfavor an SN1 reaction. Let's start by thinking about the effect of leaving group quality on SN1. Do you think that an SN1 reaction requires a good leaving group? Pause the video and determine, does an SN1 reaction require a good leaving group? Well, I hope the way you thought about that was by asking, does the quality of the leaving group affect the rate-determining step? Well, does the leaving group participate in the rate-determining step for an SN1 reaction? Yes. In fact, that's almost the only thing that's participating in the rate-determining step. The only thing that happens in the rate-determining step for an SN1 is that the leaving group leaves. So the leaving group does participate in the rate-determining step for SN1. So the quality of the leaving group matters for the rate of an SN1, and as a result, an SN1 reaction requires a good leaving group. An SN1 reaction requires a good leaving group because the leaving group participates in the rate-determining step for an SN1 reaction. Let's apply that to SN2. Pause the video and determine, does an SN2 reaction require a good leaving group? Well, the leaving group does participate in the rate-determining step for an SN2 reaction. You can see the leaving group participating here. So yes, an SN2 reaction also requires a good leaving group. So here we see a way that an SN1 reaction is similar to an SN2 reaction. They both require a good leaving group. How can you tell whether something is a good leaving group? Well, we discussed in the first video in this series that neutral chlorine, neutral bromine, and neutral iodine are good leaving groups. And we've discussed that neutral sulfonates are good leaving groups. And you should know that other neutral atoms are usually not acceptable leaving groups. There certainly are other types of acceptable leaving groups, but these are the types we've learned about so far. For example, this reaction uses a neutral chlorine, which we know is a good leaving group. And this reaction, again, used a neutral chlorine, which again we know is a good leaving group. For example, pause the video and decide, can these starting materials carry out an SN1 reaction? Can these starting materials carry out an SN1 reaction? Here's the answer. Well, I hope it was clear that no, these cannot carry out an SN1, but can you articulate why? What's the best way to use our terminology to articulate why these starting materials are not adequate for an SN1? Well, I hope you said it's because this substrate does not have a good leaving group. This substrate cannot participate in an SN1 reaction because it doesn't have a good leaving group. All it has is neutral carbons and neutral hydrogens. Well, most neutral atoms are not good leaving groups. We've never learned that a neutral carbon or a neutral hydrogen can be an acceptable leaving group. So no, this does not have any acceptable leaving groups. How about SN2? Could these starting materials carry out SN2? Answer, no. Why not? Because SN2 also requires a good leaving group, and again, this substrate does not contain a good leaving group. So these starting materials could not carry out an SN1 or an SN2 reaction. In fact, with these starting materials, you would get no reaction. These starting materials would give us no reaction. We certainly wouldn't get an SN1 or an SN2 because the substrate does not contain a good leaving group. Both SN1 and SN2 require a good leaving group because the leaving group participates in the rate-determining step for both SN1 and SN2. Let's expand on that idea. We can furthermore say that leaving group quality matters for the rate of an SN1 reaction, and that leaving group quality matters for the rate of an SN2 reaction. This means that when you use a better leaving group, that increases the rate for an SN1 reaction, and a better leaving group will also increase the rate for an SN2 reaction. And again, we can justify that based on the rate-determining step. the leaving group participates in the rate-determining step for SN1, and the leaving group participates in the rate-determining step for SN2. So the quality of the leaving group affects the rate of both an SN1 and an SN2 reaction. When you use a better leaving group, that makes SN1 reactions faster, and it also makes SN2 reactions faster. Well, we've considered leaving group ability. What about nucleophile ability? Does nucleophile ability, nucleophilicity, does that affect SN1? Do you think that an SN1 reaction requires a good nucleophile? Please pause the video and try to determine, does an SN1 reaction require a good nucleophile, SN1? I hope you paused and thought about that. I hope you thought about that by trying to apply the rate-determining step. What you should have asked yourself is, does the nucleophile participate in the rate-determining step for an SN1 reaction? Well, does it? And the answer is no. Remember, this is the rate-determining step for an SN1, and you can see the nucleophile is not participating in this rate-determining step. The nucleophile doesn't get involved in the SN1 until the second step. Here, the nucleophile is only participating in the second step, but the second step is not the rate-determining step. The second step is the easy step. The second step is the easy step. The nucleophile does not participate in this slow, difficult first step. But remember, so as a result, since it's not participating, there's no way the nucleophile can affect this first step. But remember, anything that does not affect the rate-determining step will not affect the rate of the reaction. So nucleophile quality does not affect the rate of an SN1 reaction, and therefore an SN1 reaction does not require a good nucleophile. An SN1 reaction does not require a good nucleophile because the nucleophile doesn't participate in the rate-determining step for SN1. In an SN1 reaction, the nucleophile participates in the second step, which occurs after the rate-determining step is already finished. Well, let's apply that to SN2. Pause the video and determine whether an SN2 would require a good nucleophile. Well, I hope you used the same logic. Does the nucleophile participate in the rate-determining step for an SN2? Well, absolutely, because there is only one step for an SN2. So you can see here is the nucleophile participating in the rate-determining step for an SN2. The nucleophile does participate in the single rate-determining step for an SN2. Therefore, the nucleophile quality affects the rate of the reaction, and therefore an SN2 reaction requires a good nucleophile. An SN2 reaction does require a good nucleophile because the nucleophile participates in the rate-determining step. Whereas for SN1, the nucleophile does not participate in the rate-determining step, so SN1 does not require a good nucleophile. So pause the video and ask yourself, can these starting materials carry out an SN2 reaction? Well, here's the answer. We need to check to make sure that the starting materials have a good nucleophile. The nucleophile here would be the neutral oxygen with its lone pair in the water. Is that a good nucleophile? Well, you can figure that out from our table. Notice that water with a neutral oxygen is here in the left-hand column, the poor nucleophile column. So we know that water is a poor nucleophile. So can these starting materials carry out an SN2 reaction? No, because we know that an SN2 reaction requires a good nucleophile. An SN2 reaction requires a good nucleophile. Water is a poor nucleophile. So no, we cannot carry out an SN2 reaction with these starting materials. How about an SN1 reaction? Could these starting materials carry out an SN1 reaction? I hope you answered. Well, this is a poor nucleophile, but that's okay because SN1 does not require a good nucleophile. SN1 doesn't require a good nucleophile. A poor nucleophile is good enough, so to speak. SN1 does not require a good nucleophile. A poor nucleophile is good enough for an SN1 reaction. Therefore, yes, these starting materials can carry out an SN1 reaction. These starting materials can carry out an SN1 reaction. In fact, that's exactly what our table would predict here. Our table would predict that with this secondary alpha carbon and the water nucleophile, that the major reaction would be SN1. So that's why it's important that SN1 does not require a good nucleophile. That means we can carry out an SN1 reaction with a worse nucleophile than we would need to use for SN2. How can you tell the difference between poor nucleophiles and good nucleophiles? Well, one thing you should do is just memorize those ideas from this table. Notice you should just memorize that neutral oxygen, as in water or alcohol, is a poor nucleophile. And you should memorize these good nucleophiles. What are the good nucleophiles that you should memorize? Well, you should memorize that all of these negative ions are good nucleophiles, and you should memorize that there's also some neutral atoms that are good nucleophiles. And you should also memorize that here's a few more negative atoms that are good nucleophiles. So really you should just memorize all of these good nucleophiles. Notice that things with negative formal charges are usually good nucleophiles. That's what we would expect, because a negative formal charge makes you want to donate electrons. But notice there are a few neutral atoms that can also be good nucleophiles. If you haven't done so already, now would be a good time to memorize that information from this table. You should have memorized who the good nucleophiles and the poor nucleophiles are from the table. Again, the poor nucleophiles are just neutral oxygen, that is, water and alcohol. Those nucleophiles are good enough for SN1, but not good enough for SN2. Now this table should make more sense to us. Why are there no SN2 reactions in the left-hand column? There's no SN2 reactions in the left-hand column because the left-hand column is for poor nucleophiles and SN2 requires a good nucleophile. Why are there SN1 reactions in the left-hand column? Well, there can be SN1 reactions in the left-hand column because the left-hand column deals with poor nucleophiles, and an SN1 reaction does not require a good nucleophile. So now the table should make more sense to you. It should make sense to you that in this left-hand column there are some SN1 reactions, but there are no SN2 reactions. On the other hand, notice that a good nucleophile doesn't prevent an SN1 reaction. There is a case where you could get an SN1 reaction with a good nucleophile. So it's not enough just to learn these rules. It's not enough just to learn these rules. You also really do have to memorize the table. Let's add a little bit more information to our summary here. We should know that leaving group quality matters for an SN1 reaction because the leaving group participates in the rate determining step, so SN1 requires a good leaving group. Leaving group quality also matters for an SN2 reaction because the leaving group participates in the rate determining step for SN2, so SN2 also requires a good leaving group. Nucleophile quality does not matter for an SN1 reaction, surprisingly, because the nucleophile doesn't participate in the rate determining step for SN1. Therefore, an SN1 reaction does not require a good nucleophile. Nucleophile quality does matter for an SN2 reaction because the nucleophile does participate in the rate determining step for SN2, so SN2 requires a good nucleophile. So it's good to add a little bit of this extra information here to really summarize the key factors here for leaving groups and nucleophiles. The most surprising idea here is that nucleophile quality does not matter for an SN1 reaction because the nucleophile does not participate in the rate determining step for an SN1 reaction. Now, we've seen how leaving group ability and nucleophile ability affect the rate of an SN1 or an SN2 reaction. So what is left to consider? What else could possibly make a difference? Well, the one thing we haven't considered yet is the alpha carbon. We need to ask whether the properties of the alpha carbon can affect an SN1 or an SN2 reaction. Let's start here with the SN2 reaction. Let's start with the SN2. We know that the properties of the alpha carbon can affect an SN2 because the alpha carbon participates in the rate determining step for SN2. But what about the alpha carbon matters for an SN2 reaction? This is something that we talked about in the SN2 series. We talked about the big obstacle for an SN2. what is the big obstacle for an SN2 reaction? Or what types of alpha carbons are really bad for an SN2 reaction? In the SN2 series, we discussed that the big obstacle to an SN2 reaction is steric hindrance. Steric hindrance that blocks the nucleophile from joining the alpha carbon. What is steric hindrance? Do you know what steric hindrance is? Steric hindrance is a fancy term for things getting in the way of other things. When things get in each other's way, that's steric hindrance. So if something gets in the way and blocks the nucleophile from joining the alpha carbon, that's a big obstacle for an SN2 reaction. Why? Why would this steric hindrance be a big obstacle for an SN2? Well, I hope you answered by using the rate-determining step. The nucleophile joins the alpha carbon in the rate-determining step for an SN2, so anything that makes it difficult for the nucleophile to join the alpha carbon will affect the rate-determining step and will affect the rate of the reaction. So steric hindrance that blocks the nucleophile is a big obstacle for SN2 because the nucleophile is participating in this rate-determining step. Next question, based on this idea, what type of alpha carbon would be best for an SN2 reaction, and what type of alpha carbon would be worst for an SN2 reaction? You should already know that primary and methyl alpha carbons are best for SN2, and tertiary alpha carbons are worst for SN2. I hope you know the definitions of all these terms. What's a primary alpha carbon? What's a primary carbon? A carbon attached to one carbon chain. What's a secondary carbon? A carbon attached to two carbon chains. What's a methyl carbon? A carbon attached to 0 carbon chains. I'm using less than signs here to indicate that this is the smallest SN2 rate and this is the greatest SN2 rate. So you should already be familiar with these ideas. Methyl alpha carbons have the least steric hindrance that can block the nucleophile, so they're best for SN2. Tertiary alpha carbons have the most steric hindrance, so they're the worst for SN2. They have the most steric hindrance because they're surrounded by the most carbon chains that can get in the way of the nucleophile. Methyl alpha carbons have the least steric hindrance because they're not surrounded by any carbon chains that could get in the way of the nucleophile. Remember, steric hindrance is just a fancy term for things getting in the way of the nucleophile. Now, you should also know that as a result of this, there are some alpha carbons that can't do SN2 at all. So do you know which types of alpha carbons really just can't do an SN2 reaction? The answer is tertiary alpha carbons. Tertiary alpha carbons have so much steric hindrance that that the SN2 reaction would be so slow for a tertiary alpha carbon that it's of no practical importance. So we would say that a tertiary alpha carbon can't do an SN2 reaction. We can only do an SN2 reaction for secondary, primary, or methyl alpha carbon. A tertiary alpha carbon might not literally have a rate of 0, but the rate would be so low that it's not of practical importance for an SN2 reaction. So this is something you should have memorized. Tertiary alpha carbons can't do SN2 reactions. Only methyl primary and secondary alpha carbons can do SN2 reactions. Now let's try to apply that concept of steric hindrance to an SN1 reaction. Do you think that steric hindrance would be a big obstacle for an SN1 reaction? Pause the video and ask yourself, if there's steric hindrance that blocks the nucleophile from joining the alpha carbon, would that be a big obstacle for an SN1 reaction? I hope you thought about that. I hope you thought about it by asking whether it would affect the rate-determining step. Well, remember again, in an SN1 reaction, the nucleophile does not participate in the rate-determining step. Here's the nucleophile attacking the alpha carbon, and this is happening after the rate-determining step. Well, remember, anything that does not affect the rate-determining step will not affect the rate of the reaction. So it doesn't matter how much steric hindrance there is when the nucleophile attacks this alpha carbon, because that's not occurring in the rate-determining step. The rate-determining step doesn't involve the nucleophile at all. All that happens in the rate-determining step for an SN1 reaction is that the leaving group leaves. The nucleophile doesn't participate in the rate-determining step for an SN1 reaction at all. So what we've decided is that steric hindrance that blocks the nucleophile is not a big obstacle for SN1. Steric hindrance that blocks the nucleophile is not a big obstacle for SN1 because the nucleophile doesn't join the alpha carbon during the rate determining step. Well, therefore, there's no reason to expect this pattern to apply to SN1. This pattern applies for SN2. Methyl is best for SN2 because it has the least steric hindrance. Tertiary is worst for SN2 because it has the most steric hindrance. There's no reason for this pattern to apply for an SN1 reaction because steric hindrance is not a big obstacle for an SN1 reaction. Okay, so then what is the best type of alpha carbon for SN1? If this is not the pattern that we would use, how can we determine what the best and worst alpha carbon is for an SN1 reaction? The alpha carbon does participate in the rate determining step, so the qualities of the alpha carbon do matter for an SN1. So how do the qualities of the alpha carbon matter for an SN1 reaction? Well, that's what we have to think about next. To discuss these issues, let's begin by reviewing how would you define the term carbocation. Remember that each time I ask a question, I hope that you're pausing and coming up with an answer. Here's the answer. We discussed in an earlier video that a carbocation is a carbon with a positive formal charge. That should make good sense. What does carbo mean? It means carbon. And what does cation mean? Well, we discussed earlier that we could imagine that the T is like a plus sign in the term cation. So you could imagine that this says A positive ion. A cation is a positive ion. So that indicates the positive formal charge. Now, can you find the carbocation in the SN1 mechanism? That should be easy. Here's the carbocation in the SN1 mechanism. Notice that this would be called a carbocation intermediate. Do you know what an intermediate is? An intermediate is something that's the product of one of the steps in a mechanism and the starting material for the next step in the mechanism. This is called an intermediate because it's the product of the first step in the SN1 mechanism, and it's also the starting material for the second step in the SN1 mechanism. So an intermediate is something that is used in the middle of a mechanism as a product from one step and a starting material for a succeeding step. So SN1 reactions have a carbocation intermediate. SN1 reactions have a carbocation intermediate. Next question. Are carbocations happy or unhappy? Here's the answer. Carbocations are unhappy. Of course, carbocations aren't actually people. They're not really happy or unhappy, but in science it can give us better intuition if we pretend that the chemical species are like a person. So it's helpful to pretend that the carbocation is unhappy to build our intuition. Now, why is the carbocation unhappy? Is the carbocation unhappy because it has too few electrons or too many? I hope you answered. Here's the answer. Well, remember, focus on the formal charge. A carbocation has a positive formal charge. It's unhappy because it's positive. Well, positive means that you have too few electrons. Remember, electrons are negative. Electrons are negative. The way you get positive is if you have too few negative electrons. So carbocations are unhappy because they have too few electrons. Carbocations are unhappy because they have too few electrons. You can see that from the positive formal charge, but you can also see it if you remember that a carbocation also has an incomplete octet. And again, having an incomplete octet makes you unhappy because you have too few electrons. Atoms prefer to have octets, not less than an octet. Next question. Now, this is a question that is not review. This is a question we haven't discussed previously in the videos. Do you know, are carbon chains electron donating or electron withdrawing? You might not know this, or it might, although it's probably been discussed in class. Well, here's the answer. Carbon chains are electron donating. Now, why are carbon chains electron donating? That's really not obvious. So basically you just have to memorize this fact. This is something that you can't really figure out. This is not something you can figure out based on what we've talked about previously. You just have to memorize that carbon chains are electron donating. To save time, I'm not going to explain why they're electron donating. You'll probably find an explanation for this in your textbook or lecture notes, but we're just going to memorize that carbon chains are electron donating. Remember, another term for a carbon chain that's connected to something else is an alkyl group. So another way of putting this is we could also say that alkyl groups are electron donating. An alkyl group is a carbon chain. This turns out to be a helpful fact at a bunch of different, for a bunch of different topics in Ochem. So you'll be using this again in Ochem, so you need to pause and memorize that carbon chains are electron donating. We're not explaining why that is right now, we're just memorizing this fact. Next question. Now this is a question that you can figure out, so pause the video and figure out. Do carbon chains help to stabilize or destabilize a carbocation, and explain why? Here's the answer. I hope you answered. A carbon chain helps to stabilize a carbocation, but the important thing is to explain why. And we explain by combining these previous ideas. Carbocations have too few electrons, but carbon chains can donate electrons. So a carbon chain helps to stabilize a carbocation by donating electrons to the carbocation. If the carbocation was unhappy because it had too few electrons, and the surrounding carbon chains donate electrons to the carbocation, that helps to remedy the problem with the carbocation and make it less unhappy. So carbon chains help to stabilize a carbocation. You should understand this logic, but this idea is so important that you should also memorize that carbon chains stabilize carbocations. Another way to put that is that alkyl groups stabilize carbocations. Next question, you should be able to figure out the answer to this question. Pause and decide what type of carbocation is most stable, what type is least stable. The different types of carbocation would be primary, secondary, tertiary, or methyl. I hope you answered. Here's the answer. Well, we know that the most stable carbocation is the one that, we know that carbon chains stabilize a carbocation. That means that the more carbon chains you have, the more stable the carbocation is going to be. So which of these types of carbocations would be attached to the most carbon chains? Tertiary. So a tertiary carbocation is the most stable. A tertiary carbocation is the most stable. And which would be the least stable? The one with the fewest stabilizing carbon chains. That would be a methyl carbocation. Least stable would be a methyl carbocation. Go ahead and rank the remaining carbocations. Can you rank the remaining types of carbocations from least stable to most stable? The more carbon chains you have, the more stable the carbocation is going to be. So here's the ranking. The least stable carbocation is a methyl carbocation. The most, then primary, secondary, then tertiary. Do you see how you would define these terms? How would you define tertiary carbocation? A tertiary carbocation is a carbocation attached to 3 carbon chains. As usual, a carbon chain could consist of just 1 carbon. How would you define secondary carbocation? A cation connected to 2 carbon chains. How would you define primary carbocation? A cation connected to 1 carbon chain. And how do we define methyl carbocation? A carbocation connected to 0 carbon chains. Tertiary carbocation is the most stable because it's attached to the most carbon chains. Each of those carbon chains is electron donating. So they each can help to donate electrons towards this positive charge to help stabilize the positive charge. A secondary carbocation is somewhat less stable because it only has 2 donating carbon chains. Primary is less stable again because it only has 1 donating carbon chain. Notice that the number of carbon chains is more important than the length of the carbon chains. The carbon chain here is longer than in this picture, but what matters more is just how many carbon chains there are. So having 2 carbon chains is more stabilizing than having a single longer carbon chain. So we're mainly just going to focus on counting the number of carbon chains, regardless of the length of the carbon chains. And the methyl carbocation has no surrounding carbon chains to help stabilize the positive charge. Now, when we say that these carbon chains are electron donating, well, remember that this, say, is a methyl group. A methyl group has a cloud of electrons, and that cloud of electrons is going to spread slightly in the direction of the positive charge, helping to stabilize this positive formal charge. This methyl group has another cloud of electrons, and that cloud of electrons will again spread slightly in the direction of this positive charge and help to stabilize this positive charge. Again, the electron cloud around this methyl group will spread slightly towards the positive charge and help to stabilize the positive charge. Now, we don't draw that spreading or donation of the electrons. We just kind of know about it in our minds. It doesn't change the formal charge. The formal charge is still positive on the carbon, but we should realize that that will be somewhat stabilized by the clouds of electrons on these 3 methyl groups spreading somewhat in the direction of the positive formal charge. How do we know that the clouds of electrons around the carbon chains will spread towards the positive charge? Because we've memorized that carbon chains are electron donating. Also, notice that when we say that a carbon chain is electron donating, we mean that it's donating compared to hydrogens. If you compare, say, the tertiary carbocation and the methyl group, the difference is that surrounding this carbocation, there's 3 carbon chains, whereas surrounding this carbocation, there's just 3 hydrogens. So when we say that the carbon chains are electron donating, we're comparing them to hydrogens. The carbon chains are more electron donating than hydrogens, being surrounded by when a carbocation is surrounded by carbon chains, that helps to stabilize it compared to when the carbocation is surrounded by hydrogens. So this really means that carbon chains are electron donating compared to hydrogens. Carbon chains help to being surrounded by carbon chains helps to stabilize a carbocation compared to when a carbocation is surrounded by hydrogens. This carbocation is surrounded by 3 carbon chains. This carbocation is surrounded by 2 carbon chains and a hidden hydrogen. This is crucial fundamental material for your class. Many reactions in the class will deal with carbocations, so it's crucial to know which types of carbocations are the most stable. Notice that this issue that we're discussing has nothing to do with steric hindrance. Now we're discussing an issue that has nothing to do with steric hindrance. We already know that steric hindrance is not going to be very important for SN1, so we're not focusing on steric hindrance around the carbocation. We're focusing on the stability of the carbocation, which is a completely separate issue. Now, some of these carbocations are so unstable that they basically don't form in nature. Only some of these can actually be formed in nature. So in particular, primary carbocations are so unstable that they don't generally form in reactions. We don't actually form primary carbocations in reactions because they're too unstable, too unhappy to be formed. So then obviously there should be another carbocation that is too unstable to form, which is the other one that's too unstable to form. Well, if a primary is too unstable, then a methyl would be even worse, right? A methyl is obviously even worse. So these are the 2 types of carbocations that we generally do not form in reactions. So when you're doing an Ochem mechanism, don't form any primary or methyl carbocations. If you form a methyl or a primary carbocation in your mechanism, that means you probably made a mistake in your mechanism. Generally, you should only form secondary and tertiary carbocations. There is one important exception to this. There's an important exception when you can form a primary carbocation. Perhaps we'll talk about that later in this series. But generally, usually, you cannot form a primary or a methyl carbocation. So try to carry out reactions where you only form secondary or tertiary carbocations. Another way to describe this is we could say that a tertiary carbocation is the most substituted, and a methyl carbocation is the least substituted. We'd say this is the most substituted because it's got the most carbon chains around it, and this is the least substituted because it has no carbon chains around it. So we would say this is the most substituted carbocation, less substituted, least substituted. So we would say that substitution stabilizes carbocations. Substitution stabilizes carbocations. But remember, that's actually kind of an abbreviation. When we say that, what we mean is substitution with carbon chains stabilizes carbocations. The slogan is substitution stabilizes carbocations. But what that really means is substitution with carbon chains stabilizes carbocations. Pause the video and answer this question. Well, here we have a tertiary carbocation, and here we have a secondary carbocation. Well, we know that a tertiary carbocation is more stable because it's surrounded by more electron-donating carbon chains. So in this case, the answer would be that carbon 1 is more stable because carbon 1 is tertiary, whereas carbon 2 was secondary. Next question, which is more stable, carbon 3 or carbon 4? And I'll give you a hint. The hint is this is a trick question. What's the answer to this trick question? Well, this is a trick or a trap. You should not be worrying about primary, secondary, or tertiary here because these are not carbocations. These are not carbocations, so there's no reason to think that based on what we've talked about, there's no reason to think that tertiary is more stable than secondary. So my point here is that you can't just memorize tertiary good, secondary bad. Don't just say tertiary good, secondary bad. Tertiary is good for carbocations. Secondary is less good for carbocations because remember, a carbocation has too few electrons, and carbon chains are electron donating, so they help to stabilize a carbocation. But these carbons have neutral formal charge, so they're already pretty happy to start with. They don't need electron donors around them. These carbon chains are already fairly stable. They have zero formal charge. They're not, they don't have too few electrons, so there's no particular reason why they would need to have carbon chains around them. So basically, I would just say that that there's no huge difference in stability between these. There's no huge difference in stability. I'm sure there's some small difference. There's some small difference in stability, but we don't really care about that for our purposes here. So I'll just say these have similar stability. So the point of this trick question is you can't just say tertiary is good and secondary is worse. You have to know, we have to say that what we're talking about is for carbocations. Tertiary carbocations are better than secondary carbocations. But when there's no formal charge, there's no large difference in stability. This ranking doesn't mean tertiary is always better than secondary or that secondary is always better than primary. It means that a tertiary carbocation is better than a secondary carbocation, which is better than a primary carbocation, because of this logic that we went through. Notice that this logic wouldn't apply to a neutral carbon. It only applies to a carbocation, because only the carbocation has too few electrons. Now remember that our goal from all this discussion was to determine which types of alpha carbons would be best for an SN1 reaction. We want to decide which types of alpha carbons are best and worst for SN1 reactions. And now we finally have built up the material we need to figure that out. Next question. Which types of alpha carbons are best and worst for SN1 reactions? Rank all the different types, from slowest to fastest. This is a question that you should be able to figure out the answer to based on what we've discussed so far. So pause and answer this question. Here's the answer. Well, focus on the rate determining step. Notice that the carbocation is formed in the rate determining step. This rate determining step is going to form this carbocation. Remember, that's the reason why this is a slow step. This is a slow, difficult step because it's difficult to form a carbocation. And why is it difficult to form a carbocation? Because carbocations are unhappy. They have too few electrons. So because forming the carbocation is what makes the rate-determining step slow, anything that helps to stabilize the carbocation will make the rate-determining step faster. And anything that destabilizes the carbocation will make this rate-determining step slower. The first step in an SN1 is the slow, difficult rate-determining step because it forms this unhappy carbocation. So anything that makes the carbocation less unhappy will make this first step less slow and less difficult. Well, now we can answer. We know that the easiest type of carbocation to form is a tertiary carbocation. So if we're forming a tertiary carbocation, that would be the easiest rate-determining step. That would be the easiest step one. It's easiest to form a tertiary carbocation because that's the most stable. It would be most difficult to form a methyl carbocation because that would be the least happy carbocation. The fastest SN1 rate would involve a tertiary alpha carbon. It's very easy for this leaving group to leave. It's easy for this leaving group to leave because it's going to leave behind the most happy carbocation, or the least unhappy carbocation. A secondary alpha carbon has a leaving group would have a more difficult time leaving because it'll leave a less stabilized carbocation, a secondary carbocation. A primary alpha carbon, it's even more difficult now for the leaving group to leave. It'll leave behind an even less stable carbocation, and the hardest leaving group to leave would be from a methyl alpha carbon, because this would leave behind the most unhappy, least stabilized carbocation. I'm using a less than symbol here to show that this rate is less than this rate, and this rate is less than this rate, and this is the greatest SN1 rate. So now we've accomplished our goal. Remember, our goal was to rank the alpha carbons from worst to best for SN1. So now we've seen which type of alpha carbon is best and which type is worst for an SN1 reaction. What we can say here is, so we can say that the tertiary is best because it will leave behind, when the leaving group leaves, it will leave the most stable carbocation behind. Now, if you think about it, this material means that there are some alpha carbons that can't do an SN1 reaction at all. Question: which types of alpha carbons can't do, which of these types can't do an SN1 reaction at all? Well, remember we said that you just can't form a methyl or a primary carbocation. But in order to do a SN1 reaction, you have to form a carbocation intermediate. So if you can't form a methyl or a primary carbocation, that means that you can't use a methyl alpha carbon as the starting material for an SN1 reaction, and you can't use a primary alpha carbon as the starting material for an SN1. You can't use methyl or primary alpha carbons as the starting materials for SN1 because you wouldn't be able to form the necessary carbocation intermediates. So what that tells us is that SN1 reactions only work for secondary and tertiary alpha carbons. SN1 reactions only work for secondary and tertiary alpha carbons. There is an important exception to that we'll learn, I think, later, but for the most part, SN1 reactions only work for secondary and tertiary alpha carbons. Now, when I say that SN1 doesn't work for a primary alpha carbon, that might not necessarily mean that the rate would be zero. That might not mean that you'll get zero SN1 here. It just means that the rate of the SN1 is so slow that there's no practical usefulness or importance to the SN1 reaction for a primary or a methyl alpha carbon. So now we can finally summarize what we've figured out about the role of alpha carbons in SN1. Tertiary alpha carbons are best for SN1, methyl are worst, and in fact we've also learned that actually SN1 really just is not a practical reaction for a methyl or a primary alpha carbon. It's only a practical reaction for a secondary or tertiary alpha carbon. We said earlier that steric hindrance is not a big obstacle for SN1. So what is the big obstacle? Now it would be useful. Why not? Why is steric hindrance not a big obstacle? Because the nucleophile doesn't join the alpha carbon in the rate determining step. So things that block the nucleophile are not affecting the rate determining step. So what should we say is the big obstacle? What is the big obstacle for an SN1 reaction? Well, the best way to put it is the big obstacle for an SN1 reaction is stabilizing the carbocation. The big obstacle to an SN1 reaction is stabilizing the carbocation. What I mean by that is anything that helps to stabilize the carbocation intermediate will speed up an SN1 reaction, and anything that destabilizes the carbocation intermediate will slow down an SN1 reaction. That's the most important factor to consider when you're considering the rate of an SN1 reaction. Notice that's a completely different big obstacle than the big obstacle we discussed for SN2 reactions. Again, the big obstacle to an SN2 reaction was steric hindrance that blocks the nucleophile. Why isn't that steric hindrance a big obstacle for SN1? Answer, because the nucleophile doesn't join in the rate determining step. So things that block the nucleophile don't strongly affect the rate of SN1. Instead, the big obstacle to an SN1 is stabilizing the carbocation. Why does stabilizing the carbocation matter so much for SN1? Can you answer that? Answer, because the carbocation is formed in the rate determining step. The whole reason that the first step is a slow, difficult step is because it's forming this unhappy carbocation. So because the carbocation is the thing that's slowing down the rate determining step, anything that helps to stabilize the carbocation will increase the rate of an SN1 reaction. Now, here's a question. Why isn't stabilizing the carbocation intermediate an obstacle for SN2? When we studied SN2, why did we not have to discuss stabilizing the carbocation? I hope you'll come up with an answer to that. Why was stabilizing the carbocation intermediate not an issue for SN2? I hope you came up with an answer to that. That should have been an unbelievably easy and obvious question. It's so easy, it's almost a trick question. Stabilizing the carbocation is not an issue for SN2 because an SN2 reaction doesn't produce a carbocation intermediate. That should have been obvious. It's almost so easy it's a trick question. Do you see that this SN2 reaction never produces any carbocations? What's the formal charge on carbon 3 in this picture? Neutral. And what's the formal charge on carbon 3 in this picture? Neutral. The SN2 reaction never produced a carbon with a positive formal charge. Keep in mind that formal charge is separate from delta charge. Having this delta charge does not make the carbon a carbocation. When we talk about a carbocation, we mean a carbon with a positive formal charge. This only has a delta charge, so it's definitely not a carbocation. So obviously, stabilizing the carbocation intermediate is a non-issue for SN2 because we never make a carbocation intermediate. So this is an issue that obviously has no relevance to SN2 because SN2 doesn't deal with any carbocation intermediates. So it's important to compare these two patterns for SN1 and SN2. Did you notice that the pattern of alpha carbons for SN2 is the complete opposite of the pattern of alpha carbons for SN1? The best alpha carbon for SN2 is a methyl, but that's the worst for SN1. And the best alpha carbon for SN1 is a tertiary, but that's the worst for SN2. So the pattern for the alpha carbons is completely opposite for SN1 and SN2. For an SN2, tertiary is the worst because it has the most steric hindrance. For an SN1, tertiary is the best because it will form the most stabilized carbocation. SN2 reactions don't work at all for tertiary alpha carbons. SN1 reactions don't work at all for methyl and primary alpha carbons. Another way to summarize these ideas is to say that the most substituted alpha carbon is best for SN1, and the least substituted alpha carbon is best for SN2. Substitution is good for SN1, substitution at the alpha carbon is good for SN1, and substitution at the alpha carbon is bad for SN2. Remember, when we say substitution, what we mean is substitution with carbon chains. Substitution with carbon chains is good for an SN1 alpha carbon. Substitution with carbon chains is bad for an SN2 alpha carbon. Here's a question. Think about these starting materials. Can these starting materials carry out an SN1 reaction? I hope you answered. Well, the key thing you should have noticed here is that we have a primary alpha carbon. Here's our alpha carbon. It's a primary alpha carbon. But remember, SN1 reactions don't work for primary alpha carbons because the carbocation intermediate would be too unstable. So answer no. This reaction cannot, these starting materials cannot carry out an SN1 reaction. These starting materials can't carry out an SN1 reaction because primary alpha carbons can't carry out an SN1 reaction. Next question, could these starting materials carry out an SN2 reaction? Could these starting materials carry out an SN2 reaction? I hope you answered. Well, notice here that we'd have to use the water as the nucleophile, but you should know that water is a poor nucleophile. But remember, an SN2 reaction requires a good nucleophile. SN2 requires a good nucleophile, so no, these starting materials cannot carry out an SN2. The alpha carbon's okay. A primary alpha carbon is okay for SN2. A primary alpha carbon is okay for SN2, but water is a poor nucleophile. So water is not a good enough nucleophile for SN2. So these starting materials are not good enough for either SN1 or SN2. In fact, what you would get in this situation is no reaction. Confirmed in our table, isn't it? We have a primary alpha carbon here, which puts us in the first row. Our nucleophile is water in the poor nucleophile column. So if we're in the left-hand column in the top row, the table predicts no reaction. But now, hopefully you can understand why there is no reaction. Why is there no reaction in this cell? Well, we can't have an SN1 reaction because a primary alpha carbon can't carry out an SN1 reaction because the carbocation would be too unstable. And we can't carry out an SN2 reaction in this cell because water is a poor nucleophile and an SN2 reaction requires a good nucleophile. So that helps us to understand why there's no reaction in this cell. In general, notice that there are no SN1 reactions in the top row. Question, why are there no SN1 reactions in the top row? I hope you answered. The answer is primary and methyl alpha carbons can't carry out SN1 because the carbocation would be too unstable. No SN1 reactions in the top row because SN1 isn't possible for methyl and primary alpha carbons. Question, why are there no SN2 reactions in the bottom row? Why are there no SN2 reactions in the bottom row? I hope you're answering each question. Answer, because the bottom row is for tertiary alpha carbons. SN2 is impossible for tertiary alpha carbons because there's too much steric hindrance. No SN2 reactions in the bottom row because tertiary alpha carbons have too much steric hindrance for an SN2 reaction. By the way, notice here that I'm shifting back and forth between thinking about SN1 and thinking about SN2. Students often have difficulty with that. I notice that oftentimes when I say SN1, the student accidentally thinks about SN2. Or when I say SN2, a student might accidentally think about SN1 because those names sound quite similar. SN2 and SN1 sound quite similar, but they're completely separate reactions. So listen carefully to the exact reactions that I'm talking about at each point in the video. Don't let SN1 and SN2 blur together in your mind. You need to be able to shift back and forth between thinking about SN1 and thinking about SN2, because when you take your exam, some of the questions will be about SN1 and some will be about SN2. So don't assume that each question is about SN1. Listen carefully to see whether we're talking about SN1 or SN2. You need to be able to shift gears between those different reactions and mechanisms on the test. Notice that there are no SN2 reactions in the left-hand column. Why are there no SN2 reactions in the left-hand column? And why are there SN1? Why is there SN1 but no SN2 in the left-hand column? Well, SN2 requires a good nucleophile. So a poor nucleophile from the left-hand column isn't good enough for SN2. On the other hand, remember SN1 does not require a good nucleophile because the nucleophile doesn't participate in the rate-determining step for SN1. So you can see a poor nucleophile can be good enough for an SN1 reaction. So I hope that having covered this material, this table will make a lot more sense to you. Hopefully now this table will make more sense to you. That's one advantage of covering this material. But you should keep in mind that when you're trying to predict what the mechanism will be, you can't just use these rules. These rules are not enough to predict the mechanism. You actually have to use the table. It's good to know these rules. They help you to understand the table better. But these rules are not a reliable way to always figure out the correct mechanism on exam problems. Instead, you should memorize this table and use this table. For example, these rules would not tell you what happens in this cell. We know that a secondary alpha carbon can do an SN2, but we also know that a secondary alpha carbon can do an SN1. We know that a good nucleophile is good enough for SN2, but a good nucleophile is also good enough for SN1. So based on these rules, you can't tell whether this cell should be SN2 or SN1. You actually need to have the table memorized. You need to have the table memorized to know that this cell is SN2 rather than SN1. By the way, remember that this table only gives you the major mechanisms, not the only mechanisms. So what we're saying here is that SN2 is the major mechanism in this cell. There might very well be a significant amount of SN1 in this cell as the minor mechanism. But the point is that usually for exam problems, the professor would want you to draw an SN2 for this cell rather than an SN1 for this cell. You can't figure that out just from these rules. You actually have to have the table memorized. So use the table to figure out the mechanism usually on exam problems. That means you have to have this table memorized. If you haven't done it yet, no time like the present. I encourage you to pause the video and keep writing out this table from memory until you can write out the complete table from memory. That includes memorizing the species that go at the top of each column. You can't use this table unless you know which species go at the top of each column. So memorize the complete table, including the reactants that go at the top of each column. Remember that this table comes from this handout. You can find a link to this handout in the video description box. Also, notice up here we have the summary of SN2 and SN1 reactions, and part of this summary is the big obstacle. So now we've learned that the big obstacle for an SN2 reaction is steric hindrance, and we've learned that the big obstacle for an SN1 reaction is stabilizing the carbocation. So you should have all of this material that I've highlighted. You should have all this material that I've highlighted memorized. And you should have all of this material memorized at this point. Recall that these are the different types of carbocations that we've discussed, from least stable to most stable. Now there's one more type of carbocation that we need to discuss. Please pause the video and see if you can figure out which of these carbocations is more stable, carbocation 1 or carbocation 2. Well, the answer is that carbocation 2 is more stable. So next question, why? Pause the video and see if you can articulate why carbocation 2 is more stable than carbocation 1. Now let's discuss. Now the first thing you should have thought about when comparing these is primary, secondary, or tertiary. But notice that carbocation 1 is primary, because this carbon's attached to one carbon chain, and carbocation 2 is also primary. This carbocation was also primary, because carbon 2 is also attached to one carbon chain. So that can't be the difference between them. So what is the difference between them? Well, the difference between them is that there's another resonance structure for this picture. There's another resonance structure for this picture. Can you draw that other resonance structure? Can you draw the electron pushing arrows to get to that other resonance structure? We can move this pi bond like so. And that gives us another resonance structure. Notice that according to this electron pushing arrow, carbon-2 is gaining the electrons from the pi bond, so it changes from positive to neutral. And this carbon over here is losing the electrons from the pi bond, so it changes from neutral to positive. So there's another resonance structure here. Does that make this carbocation more or less stable? Well, resonance stabilizes charges. Why does resonance stabilize charges? Resonance stabilizes charges by spreading them out. Nature prefers charges to be spread out rather than concentrated. So do you see how this is spreading out the positive charge? Now the positive charge is spread out between this carbon and this carbon. Remember that what does resonance mean? Resonance does not mean that the molecule is flipping back and forth between these two pictures. The molecule is not flipping back and forth between the two pictures. The real molecule is a blend or average of these two pictures. So the real charge on this carbon is a blend of this neutral charge and this positive charge. And the real charge on carbon-2 is a blend of this positive charge and this neutral charge, which basically means that there's really a positive 1/2 charge on this carbon and a positive 1/2 charge on this carbon. Well, that's preferable to having a full positive charge on one carbon. Nature prefers charges to be spread out through resonance rather than concentrated in one region without resonance. That's the reason why this carbocation is more stable. Resonance stabilizes formal charges. This carbocation is more stable because it's resonance stabilized. There are no other resonance structures for this picture because there's no pi electrons to move around, so this is a less stable carbocation. Okay, so resonance stabilizes carbocations, and in fact it turns out that a primary carbocation, a resonance stabilized primary carbocation, is even more stable than a secondary carbocation. A resonance stabilized primary carbocation is even more stable than a secondary carbocation. And of course, a resonance stabilized secondary carbocation would be even more stable than this, and a resonance stabilized tertiary carbocation would be the most stable of all. So remember earlier we said that it's generally speaking impossible to form primary carbocations. Well, would you expect it to be impossible to form a resonance stabilized primary carbocation? Well, no, this is totally possible. We know we can form secondary carbocations, and a resonance stabilized primary is even more stable than a secondary. So generally speaking, you should not form primary carbocations in your mechanisms, but here's an important exception. It's totally okay to form a resonance stabilized primary carbocation. Generally speaking, if you form a primary carbocation during a mechanism, that usually means you've made a mistake. But here's an important exception. It's totally fine to form a resonance stabilized primary carbocation during a mechanism. And of course, it would be even better to form a resonance stabilized secondary or tertiary carbocation. I'm not going to include resonance stabilized secondary and tertiary carbocations in this list just to keep it from getting more complicated than is necessary. But obviously, if a resonance stabilized primary carbocation is a good carbocation, a resonance stabilized secondary or tertiary carbocation would be even better. Most students don't think enough about resonance when attacking exam problems. For example, it doesn't even occur to most students to think about resonance when they try a problem like this. Most students only think about resonance if the problem mentions resonance. Well, that's not good enough. You have to get into the habit of thinking about resonance anytime there are multiple resonance structures. So try to get into the habit of considering whether resonance is a factor in any particular problem, like it was in this problem. When resonance is a factor in a problem, it's usually the most important factor. This is a problem-solving technique for your introductory Ochem class. In introductory Ochem exam problems, any exam problem in which resonance is a factor, in that type of exam problem, resonance is usually the most important factor. So, what stabilizes carbocations? We've seen that substitution with carbon chains stabilizes carbocations, but we've also seen that resonance can also stabilize carbocations. Carbocations can be stabilized by substitution with carbon chains or by resonance, or of course by both. So now I've taken what we've just discussed and added it to our notes here. Based on what we've discussed, a primary alpha carbon that forms a resonance stabilized carbocation would be better for SN1 than a secondary alpha carbon because it forms the more stable carbocation intermediate. Normally we can't use primary alpha carbons for SN1, but here's an exception. We can use a primary alpha carbon that will form a resonance stabilized carbocation for SN1. And again, it would be even better to try an SN1 reaction with a secondary or tertiary alpha carbon that forms a resonance stabilized carbocation, but I'm not going to include that in the list just to keep the list from getting too complicated. This should be enough for us to get our exam problems correct. All right, so on the screen now we have tried to summarize all of the key ideas that we have discussed in this video. Here's a summary of the factors that affect SN1 reactions and also the factors that affect SN2 reactions. We've seen how SN1 and SN2 reactions are affected by the aspects of the leaving group, the nucleophile, and the alpha carbon. And furthermore, we've tried to give an explanation for all of these facts. I think pretty much all of these facts we were able to explain in terms of the rate determining step. So now would be a good time to make sure that you have all of the ideas on the screen clearly in your notes. And now would also be a good time to make sure that you have memorized all of these ideas. I know that that's a lot of work. There's a lot of ideas here. So now is a good time to pause the video and make sure you have all these ideas memorized, because these are all ideas which there's a good chance you might see tested on exams. So pause the video and make sure these ideas are in your notes and that you have them memorized. And also, remember that you really should be able to give an explanation for all of these facts. You should be able to explain all of these facts using the ideas that we talked about in this video, and especially using the idea of the rate determining step. Okay, I hope you've worked on memorizing these ideas and that they're clearly in your notes. So what do we have to do next? Next, we have to see how to apply these ideas to problems that are typical of what you might see on your exams. And we'll work on those problems in the next video in this series. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge of $1 or more at my Patreon page. You can visit my Patreon page by clicking the link on the screen or by using the link in the video description box. Thank you.